Okay, so today we are starting Unit 8, Current Electricity. Current Electricity. So we know that we can classify materials depending on the ability to conduct electricity. Depending on the ability to conduct electricity, depending on the ability to conduct electricity, materials are classified into, so we have conductors. First, conductors. Next, we have semiconductors. Semiconductors. And third, we have insulators. Now, why does conductors conduct electricity? And why insulators are not able to conduct electricity? The reason is conductors have charge carriers, but insulators do not have charge carriers. Then we have the semiconductor. Semiconductor at room temperature, their number of charge carriers is less. And when temperature increase, then the number of charge carriers also increase. Therefore, at certain temperature, they do not conduct electricity. At certain temperature, they conduct electricity. Okay, so they are known as semiconductors. Now, what are the charge carriers? What are the charge carriers in conductors, semiconductors? It is the free electrons. So we can tell that free electrons act as charge carriers. In materials. In later, when we study electronics, you will study something called holes. So holes also conduct electricity. They are also charge carriers. For now, we are only talking about free electrons. So free electrons act as charge carriers in materials. Then what can you tell about the free electrons in conductors? It is high. Next, it is high for semiconductors. And finally, we might have one or two, we might have a few charge carriers or none of the charge carriers in a unit volume for insulators. Okay. So we can mention that at room temperature, number of charge carriers is high. Number of charge carriers in conductors is high. And in semiconductors, it is a relatively low. It is relatively low. And then we have the insulators. In insulators, there are a few. There are a few or none. If we consider at room temperature, these charge carriers are in random motion. You know, right? In your chemistry, you might have studied about free electrons. Metals, metallic bonds are cations in a sea of electrons. These electrons are free to move. So, whether you apply a field or not, these electrons are going to move. So, they are in random motion. But this random motion, if charges are moving, it is current, right? So even though due to that random motion, those currents cancel each other, therefore the net current flow is zero. So we can mention that if I consider a conductor, in this conductor, these negative charges. So the electrons are shown as negative charges. So they are in random motion. There is no specific direction or anything. They move the way they want. So right now, the free electrons in a conductor are in random motion. In random motion. Without any without without any specific direction, without any specific direction. So they don't have a specific direction. They move in the direction they want. Now, what will happen when we connect a EMF source or a voltage source? Let's look. When an electric source is connected to the ends of the conductor, an electric field E is formed across it. So this is my conductor. To the ends of the conductor, I am connecting a battery. So if I connect a battery, we know that this battery, now this side is positive, the other end it's negative. So it is going to form an electric field in this direction. Due to this electric field, what can you tell about the negative charges? The negative charges are going to move in this direction. They are going to align to one direction and they are going to move opposite to the field. So they are moving in this direction. So the important thing is they align and move in one direction. Initially, they had a random motion. Once we apply the field, we have a motion opposite to the electric field because they are negative charges. So if I mark the flow of electron, if I mark the flow of electron, the electron will leave the conductor, and here the electron would be entering the conductor. Actually, who is moving here? Actually, the electron is moving, but by convention, we used positive charges. So we are going to consider these electrons as if they were positive. So what should I do? I change the direction. So the electric current is opposite to the flow of electron. So this will be the direction of electric current, conventional electric current. Okay, up to this, have you noted? So we can mention that due to the electric field, due to the electric field, due to the electric field, the free electrons, the free electrons move or flow, the electrons flow opposite to the field. But by convention, drift of drift of positive charge, drift of positive charge is by convention drift of positive charge is considered as the direction of electric current. Okay, give me a minute. Okay, so let's write a note. Note number 1. Now we might have a doubt. In electric field, we studied that electric field cannot penetrate through a conductor. But here we say that electric field is formed inside the conductor, right? So let's put a question. Is it possible? Is it possible to set up an electric field inside a conductor? So the answer is yes. Here we already have set up an electric field. So the answer is yes. How we can do that? By connecting by connecting an EMF source across the ends of a conductor. Right? We can do that. So by connecting an EMF source across the ends of conductor, we have produced an electric field within this conductor. Now, then what about what we studied in electrostatic field? Then in electrostatic field, in electrostatics, electric field lines field lines do not penetrate through conductors. So let's understand the reason. So this is a uniform electric field. This side it's positively charged. And this side it's negatively charged. Now we place a conducting material at the center. Now let's draw the electric field lines. So this will be the electric field lines. So there are no electric field lines through this conductor. What is the reason? It's easy. Here you have positive charges. Because you have positive charge, we know that a conductor is electrically neutral. That means it has equal number of positive and negative charges. When it is placed in an electric field, they may get separated. The negative is attracted by the positive. So the negative charge accumulates on this side and the positive charge accumulates on the other side because negative is attracting the positive. What can you tell about the field inside the induced field? There will be an induced field, right? It will be towards your left. So I'll say it's E. I'll use another color. E inside. And the field outside, let's use it as E external. So what is the net electric field inside? The net electric field inside is equal because it is placed in this electric field, there will be a external electric field. So E external, this is towards our right, plus inside this, we also have a newly induced electric field, E in. That's right, E and D induced. It is towards left, but both of them are equal. Because they are equal, but E external equal E internal in magnitude. Therefore, E net is equal 0. So is the reason clear why when we place a conductor in an electric field, there is no electric field lines inside a conductor, but why here we have an electric field inside a conductor? Are the both ideas clear? Both of you have you noted? So next we have electric current. Next topic is electric current. If we take a conductor, if I consider a normal conductor, we are going to have cations. Through those cations, these electrons move. Let's say this is the motion of electron. The electrons move. So if electron is moving towards your right, then the current then the direction of current is towards our left. Will change the direction. So this is the direction of current. Then the direction of the movement of electron will be in the opposite direction. So what is electric current? Electric current is the rate of flow of charges. Is the rate of flow of charge. So let's say the amount of charge flow, the amount of charge flow in time t, it is Q. Then the amount of charge flow in unit time, that will be Q by T. So this is the definition of current, right? So we have got the equation for current. I is equal Q over T. Note number 1, I is equal Q over T. Q, it's measured in coulombs. T is measured in seconds. Therefore, current is coulomb per second. But the SI unit is amperes. Ampere is the SI unit. Okay. Next, what about current? Is it a scalar or a vector? Current is a scalar quantity. Okay, current is a scalar quantity. What is the reason? It doesn't obey the law of vector addition. You might come across this doubt later because we would be talking about direction for current. We might say the current flows in this direction, or we might say the current is flowing in the opposite direction. So we are talking about direction. Now, I'll ask you a simple question. Now you know that current is the rate of flow of charge. So you know current is charge. Now we have 2 amperes of current. Now 3 amperes of current and 4 amperes of current. What will be the resultant current through this branch? Is it 5 or 9? Is it 5 or 9? Sorry, 7. It is 7, right? Because you have to just add these 2 currents together. Okay, it is 7. When would you get 5? If you do a vector addition, you square this, sum them, and get the square root. Then only you would get 5. But it is obvious that this current is not following the law of vector addition. Okay, so keep that in mind that current is a scalar quantity, but we might talk about directions. When we talk about directions, it is not always vectors. Okay, is that point clear? So already we described ampere. I'll go through it once again. So we know that ampere is one of the 7 fundamental basic physical quantities, current, and the SI unit is ampere. So it is defined. It has to be defined properly. So this is how ampere is defined. We have 2 wires, infinite long wires, carrying current I. Both of them are carrying equal current I. They are placed 1 meter apart and in free space. So we know the attraction force between them. The attractive force between the wires is given by F is equal mu naught I square over 2 pi d into L. Let's say attractive force per unit length. Then I can bring this L down here. As it is mentioned, it's free space. I can substitute a mu naught here instead of mu. So F over L is equal, instead of mu naught, we have 4 pi into 10 to the minus 7 I square over 2 pi into, the separation is 1 meter. If I is equal to 1 ampere, because current is measured in amperes, if I is equal to 1 ampere, then F over L is equal to 2 into 10 to the minus 7 Newton per meter. So this is how we have defined ampere. Ampere is defined as the current required to produce an attractive force per unit length of 2 into 10 to the minus 7 newtons between two straight and long, straight, infinite long conductors placed apart by 1 meter in free space. So here, force per unit length placed apart by 1 meter in free space. These are important terms and this value. So other terms you can put in any order. Okay. Once you have noted, let me know.